Let's describe motion using normal and tangential coordinates. Let me first briefly overview what is normal and tangential coordinates, and then we'll solve problems. Okay, so when a particle is moving along a curve, like I've shown here, and you can describe the motion using that curve, using the parameter s, or whatever you like to call it, then the best coordinate frame to use is the normal tangential coordinate frame. Okay, and that coordinate frame is described by unit vectors. UN, UT are unit vectors. UT points in the direction in which S is increasing along the tangent, and UN is the component which is at right angles to UT. Okay, and there is something called radius of curvature, which is the instantaneous circle which you can draw about this point here. Okay, so think about question path coordinates here. So the rectangular coordinates x and y, that's fixed. That doesn't change with time, right? It's the same thing you describe the motion. The thing about this coordinate frame is that it moves as the particle moves. So UT, UN will move along the curve. Okay, so you got to basically keep track of the particle, and hence you can keep track of UT and UN. So now we got to describe the motion using this coordinate frame. Start off with velocity. Velocity is given by, if you're given the parameter s, then it's simply s dot ut, or some people just like to put v times ut. Acceleration is obtained by taking the derivative of velocity with respect to time. I will not do the derivation, but what you get if you derive this is acceleration is, there are two parts to it. One is the tangential component times unit vector in t direction, and a normal component along the normal direction. Okay, you can find what that at is. It's basically s double dot ut plus an is s dot, which is velocity, squared divided by rho, which is the radius of curvature, which I've shown in that figure. Another way of writing this is s double dot is, well, what's s dot? S dot is v, so s double dot is v dot times ut plus s dot is v, so v square divided by rho times un. Okay, one formula we've been using quite a few times in this course is acceleration is v dv ds, and that's useful if you want to find velocity as a function of displacement. You could use v dv ds with these formulas. You should remember it's only at, which is equal to v dv ds. Okay, so if you're using v dv ds, you only have to use the at to go with it. Don't use an, okay, because that describes how the path changes along the coordinates. Now the final expression I want to write down is the radius of curvature rho. Okay, so you'll be given that curve which I drew there in terms of y and x. So for example, if you're given the curve is y equals f of x, okay, that describes the curve, could be a parabola, line, so on and so forth. Rho is basically 1 plus dy dx square, the whole thing raised to 3 by 2 divided by the modulus of d square y dx square, where the mod is, if you have minus 1, it's basically 1. If you have 0.2, it's 0.2. So it basically gives you the absolute value of whatever is inside it. Okay, is that clear? Questions? Okay, so let's see how to use these expressions. You do not have to remember these. I'll give them to you in a formula which will be in the exam. The formula sheet is actually, if you go to the textbook and open the inner cover page of the textbook, the formula sheet is basically that page which I'll be giving you. Okay, so here is a problem based on what I just wrote down. Okay, an automobile is traveling on a curve having a radius of 800 feet. If the acceleration of the automobile is 5 feet per second squared, determine the constant speed at which the automobile is traveling. Okay, so let's put that in terms of variables we define. The radius is, in this case, constant. It's given to be 800 feet. Okay, if you're not given that, you'll have to evaluate the radius of curvature, as I'll show in the next problem. You're given the acceleration is 5 feet. You're not told if it's the tangential and then or the normal acceleration. So if you're given something like this, it just means that's the absolute value. It's the magnitude of the acceleration. And then you're told to find the constant speed, so you're told to find v. Okay, so let's write the expression for acceleration. It is going back to your notes, it is v dot ut plus v square divided by rho times un. Okay, so rho is given, velocity is the unknown. What about v dot? Is it given? What's v dot? Yeah, is it given or not given? It's 0, right? Why is it 0? Well, you're told that the speed is constant. So if you take the derivative of v with respect to time, which is v dot, you'll get 0. So that's why.
Then how can I have acceleration of 5 feet per second squared?
Because it's traveling in a circle in this case, so there's the acceleration due to Coriolis term. So when something is going its uniform speed, you still have acceleration because it's preventing you. It's keeping you on the circle. Right? Have you heard of centripetal acceleration? That's what it is. This is the acceleration part. Okay, so you're given acceleration, magnitude is 5, which means that v squared divided by rho is 5, and so 5 equals v squared divided by rho, which is 800. So v squared is 40,000, and so v is so it's 4,000, not 40,000. V is 63.24 units of feet per second. So this is actually a problem where this is the center, this is rho, and the particle is moving in a circle. So here, this is v dot, which is 0, and then it's going to have acceleration this way, which is v squared divided by rho. That's why the acceleration is not given. Okay, any question? So that was a straightforward problem. Let's see if we can solve this one. Okay, so a box is sliding along the curved path defined by the parabola y equals 0.4x squared. When it is at A, so A is this point, with coordinates x equals 2 meters, y equals 1.6, the speed is 8 meters per second, and increase in speed is 4 meters per second square. Determine the magnitude of the acceleration of the box at this instant. So let's put that in the terms of the variables we have. So v is 8, v dot is 4, the acceleration, well, we need the magnitude of the acceleration. So magnitude is unknown. So let's try to write the expression for the acceleration. It is v dot ut plus v squared divided by rho un. Okay, we know what v dot is, that's given to us. We know what the velocity is. We got to find rho. Okay, previous problem rho was given as 800. In this case it's not given, but we're given the curve. So we'll try to find rho from the expression which I written down earlier. So rho is 1 plus dy dx square, the whole thing raised to 3 by 2, the modulus d square y dx square. So let's find dy dx. So y equals 0.4x square, dy dx is 0.4 times 2x, and d square y dx square is, so 0.4 times 2. Okay, so let's find dy by dx at x equals 2, right? Because we want to find the radius of curvature at A, and A has a coordinate of x equals 2, y equals 1.6. So dy by dx at x equals 2 is 1.6, and d square y by dx square is 0.8. Okay. So let's sub this in that expression. One plus 1.6 square divided by 0.8. Don't forget the x. One, oh yeah. You mean here? I think I subbed in the value for x. So I get 1.6. So this is 8.39 meters. Okay, so let's take in 1. So now from 1 we have acceleration. Magnitude is, well, vector A is v dot, which is 4 ut plus v square, so 8 square, divided by rho, which is 8.39 un. That's 4 plus 4 ut plus 7.63 un. And so since we are asked to find the magnitude, it's simply the x component squared plus y component squared. (8.61). The units are in meters per second. Meters per second squared. Good catch. Okay, anything else? Is that clear? So one thing to note is you can see that dy by dx is what? It's, if you look from here, it's 0.8x, right? And dy dx is constant, it's 0.8. So thing to note is the rho, the radius of curvature, is going to be a function of x. Right? When you put that value there, it's going to vary as x. That's showing that as the box slides, the radius of curvature keeps changing because x keeps changing. So remember that radius of curvature is not constant for a generic curve. If it's a circle, you'll see you can actually do that computation for a circle. It'll come out to be a constant. It'll be the radius of the circle. Okay? So it's a function of time. It's not a constant. You'll have to evaluate it. If I ask you to find acceleration at different points, you'll have to repeat the calculation for rho at different points because the radius will change. Okay, so I think now you are all set to solve this problem. So, and we'll poll this. So determine the acceleration at the instant shown. The particle has a constant speed of 2 meters per second. Okay, so the particle is here, right at the origin. You got to find the magnitude of the acceleration and just poll your answer. Don't put the unit. Just give the numeric value. V dot square plus V square divided by rho V square divided by rho the whole square, right? and we're told that the velocity is 2 and it's constant. So v dot is 0 and rho is, in this case rho is not given, we have to find that. So rho is 1 plus dy dx square raised to 3 by 2 divided by t square by dx square. So we can find y is 2x square, dy dx is 4x, and d square y dx square is 4. And so from this we can write dy dx at what point should I find dy by dx? 0, right? Because the particle is at the origin. So x equals 0, we have 0 for dy dx, and d square by dx square at x equals 0, that doesn't really depend on x coordinate. Okay, so let's sub that in here. So rho equals 1 plus 0 square divided raised to 3 by 2, and then we have 4 for the numerator. So rho is 1 divided by 4. So I can now write acceleration is square root 0 plus 2 square divided by rho is 1/4 square. So it's really, we can get rid of this square in the square root. So it's 2 square divided by 1/4, which is 4 times 4, which is 16 meters per second square. So A is 16 meters per second square. Okay, any questions? So fairly simple, right? Straightforward. Okay. Okay, so the automobile has a speed of 80 feet per second at point A, so this is point A, and an acceleration of magnitude 10 feet per second square, acting in the direction shown. So you're shown the direction of acceleration. Determine the radius of curvature of the path at point A. So rho is the first unknown, and the tangential component of the acceleration. So at is unknown. So what we're given is, we're given the speed, it's 80 feet per second. We're given the acceleration. In fact, we're only given the magnitude. That's 10. And we asked to find rho and asked to find at. Okay, so let's try to write down whatever we know about the acceleration. So we know that the acceleration is v dot ut plus v square divided by rho un. Okay, and the magnitude of the acceleration is v dot squared plus v squared divided by rho, and the whole thing is being squared. So acceleration is given, v dot is an unknown, rho is an unknown, and v is given, right? V is given to be 80. Okay, so we have one equation there, and we have two unknowns, v dot and rho. Can we solve for those two unknowns? In fact, those are the unknowns. We have to find AT. AT is v dot, right? This is unknown. So the two unknowns are in that equation, but we cannot solve this equation because we can only solve two equations when you have two unknowns when you have two equations, right? So my question is, how can you get the second equation? Trig, yeah. How will you use trig? Yeah, so the information is given right in this figure. You're given the angle which the acceleration makes with, is actually the tangential component, right? You're given that. So you can actually find AT. AT is simply A cosine 30 degrees, right? It's the component of acceleration in this direction. This is AT. So A is given to be 10, and then I need to do cosine of 30 degrees. So AT is 6 point, how much? It will be a little more than that, right? Cosine 30 is 8.66, okay, 8.66 meters per second squared. So that's answer to part 2. Okay, so but AT is also v dot. So we know 8.66 is v dot. So we can now take this and sub in here. So A is 10 equals 8.66 square plus velocity is 80 square divided by rho, which is the unknown. So now we have one equation, one unknown. Solve for rho gives me rho equals 1280 feet. Okay, I mean if this was very complicated, here's an easier way to do this. Easier way to find rho. Okay, we've used AT, but we've not used AN. AN is simply A sine 30 degrees, right? Because this is the component in the n direction, sine 30. So AN is v squared divided by rho. A is 10 times sine 30. V is 10 square divided by rho equals 10 sine 30. So when you do this, you should get the same answer. No, my bad. This is not 10. This is 80 square. So you can check me out on that. 80 square. Square divided by 5, yeah. Comes out to be the same, 1280 feet. So there's an easier way to do it without having to do that complex square root, this expression. Okay, any questions? Yeah.